Good morning. Why don't we start off with an addendum to Chris Lincoln's birthday gathering last night, and just have a brief happy birthday APL all together. Happy birthday APL. Excellent. So I'm going to talk today about data types. And I'm focused on data types as an indication of the things that I think are most significant in APL, because data types tend to be pervasive. I'm not talking about small changes. I'm talking about a change in the entire interpreter, so that if you add, say, complex numbers, then you know that every primitive that touches a number is going to have to be changed and made sensitive to complex numbers. And sensitive in the sense that, largely in the sense they're going to do something interesting with it, rather than just test for it and say, going to do something with it. So that's sort of my definition of a data type. APL has progressed in fits and starts, sometimes because people add new functions or primitives, but the major changes, the ones that have a profound effect on the language, are the data types. All the primitives have to be reevaluated in that context. It makes us rethink all the existing primitives, maybe add a few additional primitives specific to that, but as a result, by bringing in new data types, we typically bring in new application domains. And that's really important for APL. We want to be able to expand the list of problems that we can address. And that's done in a variety of ways, but I'm focusing on data types. So a data type, as far as I'm concerned, is something that is native to the language. It's not brought in through an auxiliary processor or anything like that. It's something which has a profound effect on all of the primitives. So every one of them has to have some effect of that. So here's my list of the major data types, major data type milestones in APL. I'm going to be using this just to illustrate a few lines of APL, but largely this is not a PowerPoint presentation. And if you have questions, got a lot to cover, so I'd appreciate it if you hold them to the end, and then we can deal with them. So, not surprisingly, my first interesting data type is Booleans. I had a lot of fun with Booleans over the years, and they have a special place. My friend Philip Abrams remembers them as being in very early. He talks about Iverson's 1962 book, A Programming Language, having logical Boolean values used for compression, mask, and mesh, which not used for anymore, because we don't have mask and mesh, but I know Bob is interested in that. And John, we're going to get that in sometime. Bernanke credits Larry Breed, our dear friend, with making the fundamental, far-reaching design decision to put Booleans into the language. In a language in pretty much the same format it has been in every language that has come since that has implemented something like APL. Very compact, 1 bit per byte, one value per bit. And then there are a lot of special purpose algorithms that come along with that, as Bob talked about in his talk, and that's some of the things that make Booleans really interesting. They are ideally suited to construct loopless algorithms. And Bob put this very succinctly, I think, by saying the replacement of control flow by data flow, frequently improving performance as a result of eliminating conditionals. So that's a keen observation. You can think of the ones and zeros in a Boolean vector as the control flow. That is, the 1 says do this, the 0 says do that, or maybe it says skip this if it's like a compression. And that is an extremely powerful description of how to use Booleans and the things that you can do in it. I found a lot of uses for Booleans. Long time ago, I wrote a function called relabel. Roy might remember this. And relabel takes the name of a function in the workspace, extracts the canonical representation of that function, finds all the line labels in the function, finds all the references to the line labels in the function, not being fooled by text in a comment, and not being fooled by a comment symbol in a character vector, and not being fooled by a random extra unmatched quote mark inside a comment. So all these things you have to be careful with. And then it would rename, relabel the entire function, changing all the references and all the line labels to a consistent scheme, which for me was L1, L2, L3, etc. Because labels didn't mean much at that point. And it also supported Roy's particular scheme, which was A underbar, B underbar, etc. And there you had to take into account more than 26 labels. So, interesting function, had a lot of fun writing it. It was an entirely loopless program, not a single loop in that, using compression, expansion, all the interesting Boolean operations, so that you can do that. That's one of the things that you can do as a loopless algorithm. That's a more significant one than most, perhaps. That's what you can do with Booleans in the control versus data flow context. Another place I used it was in partition functions. I had a paper in APL 79, and I'll talk some more about that a little bit. So APL is one of the few, if not the only, programming languages to take full advantage of that data type. It's not just that the values are stored compactly, but they are accessed in a consistent manner. So V sub 3 means the third integer if it's an integer, the third floating point if it's a floating point, and the third bit if it's a Boolean. So you don't have, the programmer doesn't have to worry, or it really in many cases even be concerned about what the storage data type is. If you're not trying to do interesting algorithms like relabel with Booleans, then you just treat them as just a tiny integer, if you will. So you get high performance algorithms as well, such as summing the bits and all the other ones that Bob talked about. Booleans are ideal for use in structural primitives such as compression and expansion. And they are returned by all those primitives. I counted like 14 dyadic Boolean functions that return a Boolean. And reduction and scan on Booleans, as Bob talked about, are handled specially and very cleverly thanks to the work of Gene McDonald. The breadth and depth of the combinations of these functions operating on Booleans and returning Booleans opened up for me a wealth of algorithms that, as well as a way of thinking about data and control flow, and then data flow. One of the most important reasons for me is that, in some sense, expansion is an inverse of compression. And so I found in my code I was using expansion on the left, compression on the right. So I was doing something here, something in between, and then would do the corresponding expansion with the exact same argument as I used in compression. So there's something going on there, and I found that that relationship was significant. One example of that is the algorithm for partition plus scan. So let's define a partition vector. And a partition vector is one that is Boolean vector. Come on. It's a Boolean vector, always starts with the leading one. So this is sort of like the definition of partition then close, but it's in a Boolean context. And then we're going to work on, I'm off by one. You know, that's everything in programming can be explained by an off by one error. Come on. Everything is an off by one error if you use the right unit. So, I'm not going to be happy with that P, am I? So let's display the values here. And the actual partitioned enclose is this interesting expression. And I'm going to leave some space here. I'll also put caps lock on. Because I'm going to talk about some of the interesting elements in this off by 1. And then the tail is just this. So there we have partition plus scan. So the partitions, there are 3 of them, and the first one is of length 3, length 2, and then length 4. And the partitioning is then, I'm going to do a plus scan, and so you see the second line is 1, 2, 3, so we're going to do a plus scan of 1, 2, 3, and that's what we get in the result. The next partition is 4, 5, and its plus scan is 4, 9. And the last partition is 6, 7, 8, 9, and so we get 6, 13, 21, and 30. Now, in the nested array context, then what we're really going to do is this. And so we get the partitions immediately, and moreover, there's no interaction between these partitions. One of the dirty little secrets of doing the partition plus scan, like I did, is integer overflow. So you could have values in one partition and another partition, because they're all being merged together. We get the effect of doing a partition plus scan, but we're really involving all of the elements. And so having done that, then it's a simple matter to do a plus scan each, and then getting back to the result is a couple ways we can do it. One is we can just step on it using the flatten function, and we have the same result. Now, there's another very interesting observation about this one-liner, and that is not just that the P expand, P compress are inverses, but that the stuff in between is as well. That is, we have a plus scan on the right, and that -2 minus scan is its inverse. Now, the old-timers who remember how this originally looked, it would have a quote minus quote n delta in place of that -2 minus scan, and that was really just an inverse for, in this case, plus scan. So we've got 2 inverses interleaved like this. And this is known in mathematics, a term comes from group theory, as a commutator. And a commutator is this, essentially. And so it's a matter of applying a function, another function, the inverse of the first function, and then the inverse of the second function. And so as a, no, I don't need that. So the commutator is this, we'll do this as F inverse G inverse FG. So that's what a commutator looks like. And when I get around to it, I may well pick a symbol and make that happen. I have to put in inverses first. You know, I did inverses in the original NARS system ages ago, and all the other things that I got involved with, I just never got around to doing inverses in this NARS 2000. This is closely related to the dual operator, which is essentially everything, beep yourself, everything that had there except for that leading F inverse. And now dual is a really interesting operator, but you can see how closely related these two are. Dual is an even more interesting operator and more commonly found. In fact, you do duals all the time in your life. If you were to open a drawer, change the contents, close the drawer, then that's opening and closing are inverses, and the thing that you do in between is what you're doing. You're doing a dual at that point with respect to opening the drawer. You're going to find that everywhere. You also find it in programming. Someone pointed out to me the other day, something I hadn't realized as an example of dual, which is the Pythagorean metric. And so you have a n-dimensional vector that represents a point in space. You want to find the Pythagorean distance from the origin. Well, you square all the elements, you add them together, and then you take the square root of that. Well, that's just doing a addition, that is a plus reduction, dual squaring. And so we do the first operation, square it, add them together, that's the second operation, that's the f, and then g inverse is square root. So dual is everywhere. I'm still looking for more examples of commutators, so please let me know, because I think there are more of them out there. I just perhaps haven't been observant, and perhaps I can co-opt some more eyes on your part to be able to do that. So this is just another example. I got a little far afield from Booleans, but this is just another example of what, to me, makes APL so interesting. Discovering templates such as this, and seeing how I can add that to my toolbox. And the thing that I love about APL, among other things, is collecting these templates, being able to recognize them in terms of when I'm thinking about the problem. Then I want to be able to have a set of templates such as dual to see what it is I'm doing, so that I know that if it looks like I'm doing dual something, then that first operation that I'm doing is going to have an inverse. And so I'm right away starting to think about what the inverse of that function is. Being able to incorporate these ideas into your toolbox is going to make us all much more proficient programmers. Of course, we'll be able to recognize these situations and say, I know what that template is. I've already used it, I'm familiar with it, and now I can put it to use in this particular example. So the importance of the data type is, as indicated, that it was in APL 360, early version of APL, and it's been in nearly every major implementation of APL since then. There's some exceptions, but for the most part, Booleans are a very significant data type. They are compact storage, they have a host of fast special purpose algorithms, and most importantly, they occur often enough in programming that all the work to do fast special purpose algorithms is worthwhile. Now, initially, APL systems were limited to uppercase italic characters and uppercase underlined characters. And that grew and grew, and we got rid of the underscores, we added lowercase, and we added a lot of special characters and such. But because each vendor was doing it a little bit differently, in fact, we all still have different quad AVs for the most part, this, while not completely shutting down, it hindered the transmission and transference of programs and data from one APL system to the other. And then when the GUI came around, the graphical user interface, APL vendors put in APL fonts, and because they were also based upon their own quad AV, then we had those incompatibilities between vendors. They were certainly worked quite well for that vendor, but we weren't looking at the bigger picture. Along came Unicode with all the APL characters in it, in fact, more than we ever wanted in terms of characters. And eventually we could display APL on pretty much any device that could display Unicode. Now, we have APL fonts, specifically APL Unicode fonts, not because we just want to be different, but they're much more attractive to us than just getting some random splat on a screen that says it's an epsilon, but you could fool me on that. So the significance there is, as standards are supposed to do, they bring together competing and disparate views, and now we have Unicode standard with all the APL characters in it, and we can transfer things, at least in that respect, much more easily. Also, I'm sure you all remember that in the past, APL has been criticized for having all those funny symbols. Thanks to Unicode, we now have the perfect answer to this. We look them in the eye and we say, you think we've got funny symbols? Let me show you Unicode. So now we have an answer. Nested arrays are near and dear to my heart as they represent my first foray into APL system programming. I started with reading Jim Brown's doctoral thesis, A Generalization of APL. I joined SDSC in 1971, and I think Jim's thesis came out the same year. And so I don't know how that happened, but a bunch of copies circulated amongst SDSC, and I just took off with it. I thought, this is a great idea. And so I moved to California in 1978 to work for Roy Sykes in his department out there. And then a couple of years later was called back to company headquarters in Bethesda to design our nested array system. And I was tasked actually only with designing nested arrays. And so when the question came up of who would implement it, I just raised my hand. And so that's how the first nested arrays research system, NARS, was born. My first task was to learn IBM assembler code. Now, they say that in order to learn a new programming language well, you need a good starter project. And so mine was nested arrays. The significance of nested arrays is that they remove the shallow rectangularity requirement that we have in APL. Shallow meaning we were dealing with just one-level arrays. Yeah, there's a minor difference between scalars and non-scalars, but they're all both essentially shallow. And then the rectangularity aspect of it, well, we all remember the days of trying to jam non-rectangular data into rectangular arrays. So the classic example is the names of the months. For some reason, they're not all the same length. And so we had to pad out, put them in a matrix, and then be able to deal with the fact that some of those months have some extra blanks, and when we display them, we're probably going to want to get rid of them. Of course, in a nested array, we now would have just a 12-element nested vector of character vectors, and each one of the character vectors would be of the proper length. No need to have any padding characters. One of my favorites, of course, was, as I mentioned, the partition functions, where that was another way of dealing with nested arrays, so that you could partition an array, or at least provide a partition vector that would indicate how this array was to be partitioned, and then be able to apply some operation. And I had a whole slew of operations that you could do well above and beyond plus scan, and then be able to apply that to the individual elements. So in sort of a twist of the phrase, nested arrays led us into the woods so we could see the trees of data that a nested array represents. Our terminology changed too. The arrays we were so used to before that, we now are calling simple, which is akin to being shocked to learn that all your life you've been speaking prose. We now call them simple. The new ones are nested. We also had heterogeneous arrays where we're concatenating scalars and numbers. We have a whole bunch of functions, one new operator, the each operator. But the data type is one of the, in fact, of the data types I'm talking about, it's the only one that's really structural. The rest of them, aside from the characters, are new numbers. So overall, of all the extensions made to APL over all the years, I consider nested arrays to be the most pervasive. It's the only structural one of the types that we're dealing with, and so I consider that one the most significant. Nested arrays weren't without controversy, as there were two competing definitions. You may remember the floating versus grounded. And They differ in many ways, but most significantly as to whether the enclose of a simple scalar returns a new array or the same array. So I was in the latter camp, where the enclose of a simple scalar returns that. That's perhaps influenced largely by Jim Brown's thesis. And that I still don't have a good mnemonic for whether I was in the floating or the grounded, but I do remember at least what the enclose of a simple scalar is. Maybe afterwards someone can help me explain floating versus grounded. And it looks like all of the major APL implementations now use the, I think it's called the floating system. And I'm not sure that's so much a consequence of it as a better definition. I'm not sure that's the case at all, because there are a lot of economic factors as to why that one, the other definition is not very prevalent nowadays. Arithmetic progression arrays, somewhat controversial, I guess, but I put them in and wanted to see how it works, and I'm really pleased with them. They're an outgrowth of the VSAPL structure of arithmetic progression vectors. And the shift to an arbitrary rank shape and such is really straightforward. The data portion of the storage of an APA is fixed size. The data portion just has assigned offset and assigned multiplier, a couple of, in our case, 64-bit integers. The effect of doing a reshape on a singleton, numeric singleton, integer singleton, is that it also generates an APA, arithmetic progression array. So it's not just monadic iota and operations on monadic iota, such as multiplying by an integer and adding an integer offset, things like that. So it means you can represent huge arrays. Let's see. I haven't tried this in a while. So there's a huge array, but of course it really isn't. That's just an arithmetic progression vector, and we don't have to go through all the elements of an arithmetic progression vector, particularly one that has a multiplier of 0. We can calculate that fairly quickly. So there are various ways it can be used. And one of the ways it can be used by system developers is to deal with elided indices. So if you're doing indexing, you've got that bracket semicolon, you have an elided index in there. So that can use an arithmetic progression vector there so as to avoid having to deal with the special cases of having an elided array coordinate in indexing. Complex numbers are another important data type, moved APL into the world of two-dimensional numbers. And here, dimension has a couple different meanings. There's the APL dimension, where we're dealing with first coordinate, last coordinate, etc. And the mathematical definition of dimension, where it's dealing with a number of coefficients to represent that number. So a real number is one-dimensional, a complex number is two-dimensional, etc. And I'll talk about the other ones beyond that. Complex numbers are an optional feature of the extended APL standard, but I think all the major APL implementations have them, because it's important to pick up another application domain used in principally electrical engineering, electric circuit analysis. Perhaps the old-timers here remember Paul Penfield's Martha package that had to simulate the effect of a complex number by using a little data structure. Hypercomplex numbers are numbers that extend the real and complex into the 4-dimensional and 8-dimensional numbers. So that's quaternions and octonions. Thank you. Yeah, I think so. The same thing about those. Mathematicians have defined such dimensional numbers beyond octonions, but they have a fatal flaw that's called zero divisors. And by that I mean you can have two non-zero numbers such that the product is 0. And so that's a zero divisor, and that makes it more difficult to deal with them from a theorem-proving sense. It's one more exception. Quaternions are used much more than you might think. If you write video games, you're probably going to be using quaternions. That is, they're ideal for doing a combination of scaling, rotating, translating, and the like, all in one operation of multiplying by a quaternion. So that proves to be much more efficient than doing the old approach, which was use a 4x4 matrix, 16 numbers in total, called a homogeneous coordinates. And then you could stick an extra column of zeros on your 3 column for 3-dimensional numbers, multiply it by that 4x4 matrix, and that gives you the effect of doing rotation, scaling, translation, etc. I found these hypercomplex numbers to be quite fascinating. I've written numerous papers on it, and they can be found on my website. The significance of quaternions and octonions to APL user is unclear. I don't think any system developers in the room is going to be saying to himself, yeah, I really should read up on that so I can implement it. No, wait. Remember, I'm the pioneer here, and as with all pioneers, you can recognize them by the arrows in their back. Multi-precision numbers, I think, are great ideas. They allow APL to handle a couple of new classes of problems. Ones that require an exact, as in infinitely precise solution, and ones that require a highly precise solution, higher than the 53 bits you're going to get from the IEEE 64-bit floating point number. And those are two uses. So they extend the fixed precision integer floating point types into the multiple precision domain. And they have very similar relationships, so that as in APL now, you are aware that an integer argument might produce a floating point result, and it just naturally gets promoted from integer to floating point. In the same way, multiple precision integer rational is automatically promoted to multiple precision floating point. And that's a great benefit, because it means you need to just start with the multi-precision integer rational, and then the system will take care of converting it to a multiple precision floating point number if necessary. Maybe you're lucky and you'll not have to do that at all. So let's take a look at how that works. Let's say, so we have 100 times, that's not times, times iota 2, big number. And then raise that to as an exponent on 2, and you see we've lost a lot of precision. However, if we put an x on the end of that, we get what looks like the same values, but now we have 100 and 200 as multiple precision numbers. And if, as before, we raise that to as an exponent on 2, then we're getting the full accurate result, infinitely precise. So these are, although it looks like an integer 2, it's really being stored as a rational number, numerator 2, denominator 1. So when I talk about a multi-precision integer, I'm talking about a really one with a denominator. So there's all sorts of things that you can do with this. Let's say, not that one. So if we do a matrix inverse, then we're going to get that. However, if we make that an integer, then we're going to get exact results. And moreover, if we, you know what happens when you multiply a matrix with its inverse, you get the identity matrix. Does that look like an identity matrix to anybody here? Instead, that looks like an identity matrix, because, and we didn't need to change the right-hand A to a B either, because the only thing that matters is that we get an exact result out of domino. I have plenty of favorite examples, but not as much time as I'd like. So let's skip on to multi-precision floating point. And you might not appreciate how much you need this, but you really need it, and you don't know it, because few of us are really numerical analysts, and few of us have enough skills to be able to look at an algorithm and say, okay, the precision that you have natively in IEEE floating point of 53 bits, that's enough for this algorithm. But for the rest of us who are not really sure, not able to make that kind of comparison, then that's why you need multi-precision floating point. And so it's a matter of then changing your algorithm, which is quite trivial. You add an x to the end of every constant. So for example, if you've got this, well, clearly that's a floating point number. But if we put an x on the end, now we've got a rational number. And the reason is that every decimal value we enter in APL is really a fractional value. It's a quotient. It's a rational value. And we can also notice that if we change that 1 to a 2, then we get the corresponding number, but the system is automatically taking into account deleting common factors. So there's plenty of use for this, and this is implementing this stuff is a big job, no question about it, because it touches every primitive, and every primitive that does numeric calculations is going to duplicate that code in multi-precision arithmetic. At least one multi-precision floating point. You may also need to duplicate it in multi-precision integer rational. So the significance is that it allows us to address new classes of problems that require more than the fixed precision of integer and floats. Now, I've had both forms of multi-precision numbers in my implementation of APL for several years, and by example, I have tried to convince Dyalog to put them into their implementation. Well, now that you are all convinced that we need multi-precision numbers, I want you to turn to the nearest Dyalog representative, and I want you to say to them, we need multi-precision numbers. All right, everybody after me. We need multi-precision numbers. Good. I'd be happy to accept that trade-off. So as you can infer, I believe data type is king. There have been many individual functions and operators introduced over the last 50 years, but I see these data types as having driven the most significant changes in the language, and as well as making it more and more relevant to modern problems. I have been honored to be present at the start of many of these events. The last 47 years from when I was first introduced to APL in 1969 have been an exciting adventure, and has introduced me to another way of thinking about programming that's unlike anything I've seen before. I heard you the first time. So, although I programmed in many other languages since 1969, APL is the one language that I keep coming back to. Even after I left SDSC and my wife and I started our own software company, I was still going to APL conferences and certainly APL standards meetings as a secretary. Saw the ANC APL standard all the way through and the ISO standard partway through. I've used APL in our software business on a number of occasions where I was trying to write an optimization algorithm to put programs into, you may remember, high DOS memory. And that taught me that once you've learned to think of, in APL, computer programming and thinking logically in general is so much easier. Thank you for listening.